Okay, so I'll formally be starting today's proceedings, right? So first I'll give you a quick recap of what all we had seen in the first lecture, right? So if you remember, we started our discussion with what is AI, a timeline of AI, and then we saw how AI is related to machine learning and how machine learning is related to deep learning, right? And then we saw basically your course contents and what type of network to use in what type of problem, right? So basically we actually discussed that if you have a given problem, what is the right network for that problem? Of course, we have not seen them yet. They are the course contents, but I just told you the names of different networks that we'll be looking at in this course, right? Okay, then we had seen some standard data sets which are commonly used by the deep learning community, right? And I told you that the idea is that whenever you come up with a novel technique, so it's always a good idea to evaluate them on a benchmark data set so that you can actually tell how good your system is once compared to the existing solution, right? Okay, and then we had some installation guide, right? In which I told you how you can install TensorFlow, how you can create an environment, right? And we'll do a little bit more of that today. And this was basically your, you can say, the first 2 hours of discussion were dedicated to this. And then we discussed some preliminary concepts which will be frequently used within our discussion, right? So I think I told you about derivatives. What are derivatives, right? How you compute them numerically. And then we saw if we apply calculus formula, we get the same thing. And then we had seen what is sigmoid, what is softmax, and you had also seen what is one hot encoding, right? So I think this sums up pretty much what we had done previous week, right? There is one small thing which was left last time, so I'll start with that. So if you remember, we had seen sigmoid, right? But frequently when you are dealing with neural networks, you need to compute the derivative of the activation function, right? And most common activation function is sigmoid. So in the beginning, I'll just, you can say, derive the derivative of sigmoid once, so that later on, once we are in the subsequent weeks of the semester, I don't have to repeat it again and again. Okay, so let me just clean this and then we continue. Okay, so if you remember, let me write the expression for the sigmoid function. So last time we discussed that sigmoid is something like this. Okay, so whatever value of x you plug in this function, the good thing is that it will always map your output in this range, that is 0 to 1. Okay, whether you have a very large value or a very small negative value, 1 million, 10 million, 100,000, 5, any value, the range would always be 0 to 1. Okay, so basically this is a common activation function that we use in neural networks, and whenever neural network is learning, as we'll see today, we often need to compute derivative of this function. Okay, not only this function but any activation function we are using, but I'm giving you example through this sigmoid function. Okay, and in most of the books, instead of f of x, you will also see this notation, sigmoid of x, right? So you can use any of these, either you call it f or sigma or whatever you want to call it. Okay, so the objective is that we want to compute derivative of this. Okay, so I'll be deriving it, but if you are not familiar with calculus, you can actually ignore this derivation, but at the least I expect you to to know the final result. Okay, if you understand the complete derivation, well and good, but if you don't have a background of calculus, you can only focus on the final outcome that we achieve. Okay, so let me just write. So this is the symbol for derivation. We want to take the derivative of sigmoid of x with respect to x. Okay, so I write, and here I write 1 plus e raised to power minus x. So instead of 1 over, I am writing it like this. Okay, power minus 1. Let me just change the color of the pen so that it's more visible to you. Okay, so now we take its derivative. So what happens in derivative, this power comes here, so it will become minus 1, and then I will have 1 plus e raised to power minus x. This will become minus 2. And then you have to take the derivative of whatever is in the parentheses, right? So derivative of 1 is 0, and derivative of e raised to power minus x is minus e raised to power minus x. Okay. So now what happens, there are two minus signs, so they will cancel it out. So it will become something like e power minus x over 1 plus e raised to power minus x whole square. Okay. Now, just for the sake of simplification, I can multiply any number with 1. It remains unchanged, so I have written it like this. Okay, and this allows me to split this into two expressions. So I can split it into 1 plus e raised to power minus x and e raised to power minus x divided by this thing. Okay, so it is exactly the same thing. If you multiply them together, you get back from where we started. Okay. Why we are doing it? Because we want to simplify things. Okay, now further what I can do is that, let me just change the color. To this term in the numerator, I can add 1 and subtract 1. Okay, so I just put a plus 1 and minus 1. Again, they cancel it out, they cancel each other out, so it does not change anything, but it allows me to actually split it further. So this is this term. Okay, and then what I can do, I can split it into two terms, this part and this minus 1 part. Okay, so this will become just hold on 1 plus e raised to power minus x over this and this thing. Okay, so what we have done, we have simply split it into two fractions. This part is here, and then minus 1 over this part is here. Okay, so both of these will cancel out and I get a 1. So what I get here is, it will become 1 over 1 plus e raised to power minus x, 1 minus 1 over. Okay, now if you closely look, we have arrived from where we had started. Okay, so what does that mean? This term, this is actually f of x or sigma of x, right? And this term is also, if you see here, this is actually f of x or sigma of x. So I can actually write it, I'm going here, as sigmoid of x or f, whatever you like, 1 minus sigmoid of x. So this is the key expression that you should remember, that the derivative of sigmoid function is that function into 1 minus that function. Okay, so let me just highlight it. This is the key, you can say, expression that I'll be using frequently whenever we are talking about, you can say, neural network or learning of neural network, right? So if you have some background of calculus, you understood how this derivative is being taken and how we are doing all these simplification. It's okay, it's good rather. But in case you are not able to follow these steps, I don't mind it, but this is the expression that you must know. Okay, I won't ask you to derive it in an assignment or an exam, right? But this is the expression that is expected, that at the least you should know this. Okay, sometimes you will see this notation and sometimes you will also see this notation. Okay, maybe we can use the symbol f or sigma, whatever you like. Okay, so this was one small concept that was left from last week, right? So if you have any queries related to the derivative of sigmoid, please let me know, and then we start today's discussion.